Let me again take control. I take the opportunity to welcome all the participants. Good morning, good afternoon, or good evening, depending on the area where you are living. Today we have another of the several webinars which GMI is offering since a couple of years. We started with the COVID, and since we received a lot of feedback, positive feedback from the participants, we decided to proceed to share our knowledge. You know, I have to ask you, please, because I have no control. For some reason, I have no control. If you can go back.
Nope.
Okay, here we can. Can we start? Because you see also the participant coming in.
Yes.
If you believe we can start. So again, welcome to everybody. I was just saying that GMI is offering several kind of webinar on different topics, and today's different topics, meaning we touch functional safety, we touch intrinsic safety topics, we touch application topics when it comes to apply certain apparatus like safety relays. So we share our knowledge with whom decide to participate to our webinar. Today the topic is in relation to functional safety. And I'm proud we have here together, I have here together with me, even in two different locations, Tino. Just a short introduction of myself. I'm Mauro Perego. I'm a Global Sales Director of GM International. And today we have Tino van de Capelle, our functional safety expert. Luckily, I know Tino since many years. I think we are around 30 right now. I had the chance to cooperate with him for several years. And today we will touch a specific topic of functional safety, something to do with the safety function repair and restore. And we will do consideration on unavailability of the safety function. I will not talk anymore about the topic because I will leave the expert to do that. So we can proceed to the next page, Tino. I'm just taking a few minutes again of your time, just introducing GMI, just shortly. GMI is an Italian company providing to the market field interface. And the field interface provided by GMI cover two important aspects of safety. One, it is intrinsic safety, and the other is functional safety. So you find GMI devices on DCS package, fire and gas package, and you find GMI in several industrial sectors, mainly oil and gas, but also petrochemical, pharmaceutical, and so on and so on. We have 40 years of experience, which we can share to our customer, to our partner. And as mentioned, we are Italian company and we have an internal production. So everything 100% is done in Italy, but of course, we are available and present all over the 5 continents of the world. Before to proceed shortly, I want just to mention and confirm you that this presentation will be available on the YouTube channel, and any participant will also receive a PDF copy of that. So, so you will get it. Let me proceed. Just here a few numbers about how many offices we have around the world, how many we are. We have many installation, many experience to share. And also I want to mention that as expert of functional safety, expert in intrinsic safety, we provide also a way to share our experience, and we do that with our webinar, of course, but we do that also with training. We provide functional safety training, for example, together with Tino. But I will leave later on. There will be a moment where we also share this information, so we can proceed so that we can go straight to the point of today's topic. Few words again. Yeah, GMI is a safety company. That means the target of our product is to contribute in reducing risk for company, for people, for the asset of a company. That's why the quality cannot be compromised. So we do everything here in Italy, and everything before getting out once it is produced, it is tested 100% before to reach our customers. So we have such a confidence on the quality of our product that we provide 5 years warranty upfront without requiring for any extension. Let's go to the next few slides again before entering into the topic. Yes, this is just one slide showing up the certification we have. Of course, we have to produce with a high level of quality, so we have all the necessary certification together with all the necessary international certification which are required by the market. If you see on the right side of the slide, you have a lot of marks which identify also the local certification requirements. So even we produce in Italy, our products are certified to be installed almost everywhere it requires a specific certification. Go ahead, Tino. Okay, this is shortly the portfolio of GMI. As mentioned, that we cover we cover the requirement of intrinsic safety or functional safety, or both of them. So we have intrinsic safe barriers, safety relays. We have isolator, safety-related isolator, for example. We have power supply systems, a multiplexer system, which can be installed up to zone 1 in hazardous location. We have the customized termination board for an easy connection to the main SIS or DCS system. We have HART multiplexer, surge protectors, as well as loop indicators. And as mentioned before, this is not a product, it is not a hard product. We have and we share our experience on intrinsic safety and functional safety through training, through webinar, through several ways. So even a customer is interested in going deep on a specific topic, just drop us an email and we can manage to support you. And of course, we provide consultancies on these two important topics. So let's proceed fast to the next slide. Yes, this is a short list of customer we have divided by grouped by system vendor, EPC contractor, OEM, and end user. And as mentioned, this is just a short list for your reference. You could immediately detect that we are worldwide and customer and considered by main customer. Promised to be short. Now I leave the speech to Tino to enter in a deeper presentation, deeper discussion on safety function. Just want to mention that while Tino is presenting, you have the chance to raise questions. I will monitor the screen, and if there is any question, I will interrupt Tino in the right moment to provide you the answer. And finally, last thing to say. At the end of the webinar, at the end of this presentation, we have foreseen a question and answer session. We collect some questions during the registration, and we are going to provide you a feedback. Tino, it's you. It's your time.
Thank you, Mauro. And thank you, GMI, for giving us another opportunity here to provide a webinar. Mauro, can you just maybe turn your volume a bit down because I hear some echo? Maybe it's coming in back to the microphone, but it doesn't really bother that much. Anyhow, the topic for today is the, as the title was saying, safety function repair, restore, and the unavailability prediction. And I'm focusing more on the availability or the unavailability prediction of your safety function. And one of the topics for today will be, when do we find out that my function is no longer working? There are two specific times that we can define in there. And then will be the question, how long does it take you or the company to repair it to as good as new or to a working or functioning safety loop again? And that will be the topic for today, as said. Mauro already mentioned there's a Q&A box, so if you do have a question, you can write it into the question box. Mauro will monitor that. During our webinar, we also have a poll question. That means that we would like to see how alert you are or how much of the topics that you are following. Concerning the topic for today is, of course, in relation to functional safety, and we will refer to the leading functional safety standard for the process industry, which is the IEC or the ISA 61511. We are referring, of course, to the second edition, which was released in Europe 2016/2017. Back in US, was released in 2018. There is no specific life cycle phase which I'm targeting. It's like an overall topic because we have built already a safety function. It is working in the field. And when do we find out it is no longer working correctly, or how long will it take us to repair it? That's the topic. I take you back in time. I take you back to before the edition 1 was released of the other standard, which was called the IEC 61508. Let me just move a few windows, as I'm working on a smaller screen today and I'm a bit lost. Anyway, the safety function in the old days, before the IEC 61508 edition 1 1997 was released, was purely measured on a quantitative approach, which we used to call in English the requirement class or the RC classes. But however, in the international world, many often older safety engineers would refer to a K class. And a K class was an abbreviation for a German word called the Anforderungsklasse, which means in English the requirement class. And we used to have 8 classes in that, and that came from the standard called DIN 19250. So when an engineer or when a client wanted to have a, let's say, safety system, and I'm mainly focusing here on the before 1997 was on the safety PLCs, they were buying a qualitative safety system or safety PLC. They were connecting instrumentation because at that time SIL or safety integrity level did not exist. And all the client was worrying about was, can you provide a system with a safety availability of 99+%? In other words, they wanted to have the safety system working and it had to be available. In that time, the MTTR was standing for mean time to repair, and that was like a general concept for most engineers, that we were estimating that how long will it take us for the system to repair it, to reveal first the failure would be that either we would reveal it the moment we're trying to test it, or it would revealing himself when it is too late. In other words, there is demand coming on the safety function. The safety function is not working. And from then onwards, we were counting a MTTR, which was called the mean time to repair. Just trying to move forward. The old standard, which I just referred to, called the DIN V 19250, is obsolete since 2004. However, you may have seen a similar picture like this, which is called the risk graph. And there were like 8 levels of Anforderungsklasses in here, which was 1, 2, 3, 4, 5, 6, 7, and 8. 7 and 8 became in 1997 with the introduction of the IEC 61508. That became SIL 4. 5 and 6 became SIL 3. AK4 became SIL 2, and for AK2 and 3, that was SIL 1. For AK1, which was referred to here on the top, there was no SIL integrity level foreseen for that. I'm pretty sure that today, since we are already in 2023, so it's for long that we are already talking about SIL integrity levels. Majority of the engineers, they are actually talking about SIL levels, and they are referring also to what is the availability of that SIL level. Simply speaking, for those who are all new to this, I explained it the following. When you have a SIL2 integrity level of loop, of safety loop, well, that SIL2 loop will be 10 times more available than your SIL1. In other words, the SIL2 will fail 10 times less than your SIL1, and the availability is expressed in the safety unavailability. So we just do the opposite of what we used to do in the older days. We used to talk about the availability. Now we are expressing it in the unavailability. I'm pretty sure all your safety compliant subsystems, interfaces, or devices that you may buy, that the manufacturer, like also GMI, they will give you a PFD number of that specific subsystem under specific conditions to be used, will be representing a certain number. On the right-hand column here, that is the easier way to explain, that is your risk reduction factor. For those who are familiar with the topic risk reduction factor, what we actually are trying to do is we are trying to reduce the likelihood or the frequency of the hazard happening. In other words, when we are doing our estimate how frequent the hazard will happen, we will be checking with the end user on the tolerable frequency, what is tolerable, what is acceptable. If we have to reduce it, we are reducing typically in a band between 10 to 100, more than 10 to maximum 100 would be a SIL1. So when you divide 1 by 10, that is again your unavailability here coming on the left. Now, how did we estimate back in the days and use the MTTR? And I give you here the most default numbers, which I still see today in 2023 with some of the, let's say, SIL verification, let's say, documents, reports that clients will show us on the project. We used to have a default number between 8 hours, 24 hours, 72 hours, and 96 hours. And on the 96 hours, this was coming from a very long weekend. And this came in the old days, it was based on a specific example which they used on an offshore platform where they had to first find the person who was on duty to go visit the offshore platform to find the spare parts, etc., etc. So the whole theory that they were coming to 96 was purely on a long weekend. 24 hours is one shift change, 8 hours was in the same shift, and the 72 was for a 3-day period where they were counting that is the worst case before it will be repaired. Of course, no one was really wondering, is the spare parts in stock or not? They were purely estimating on the availability of the engineer to go to repair it. So after some research, and I'm referring here to a document, which is a document from the ISA 84 committee, which is a safety division of the ISA. And in that document called report number 2, which has been released in a newer edition in 2022, I'm referring here to a specific figure. So that is the reference. Although it is a copyright, I'm just showing you what the principle is of this figure. The old MTTR only started from the moment that you knew that the safety function was not working. The question is, when do we find this out? Do we find this out automatically? And that will be the topic for today, by kind of diagnostics built in your subsystem. Or do you only find out when you're doing your proof test? When you're doing your proof test, of course, the question is, how long will you take before you will do your test? The normal proof test intervals today that we hear in the market are easily starting from 1 year, which is 12 months. 1 year means also 8,760 hours. So you will see that in the estimate of average of unavailability, they will take the maximum 1 year proof test interval divided by 2, and they will purely estimate that minimum half of your time, your system is still working. The other half of the time, your system may not be working. Anyhow, if you look here on the MTTR, which used to be called repair, it was starting from the time you find out it was not working. So you detect it or you find it out. You need to prepare yourself. That is a certain delay. Prepare yourself means that you have to find out, do we have it in stock? You have to fill in the work permit, talk to the production people, etc., etc. Then you have your active time for repair itself. And of course, there's a big difference if you have to replace a, let's say, a valve which is stuck open, and you have to replace with another valve. That will certainly take you longer time than you, for instance, would take the shortest time, like an example, a glass fuse. If a glass fuse in your terminal strip is no longer available and you lost the power to a specific loop, well, certainly to replace a glass fuse, it will go faster than you will replace a final element. Therefore, all these times on all the safety loops cannot be all the same as 8 hours or 24 hours. We have to think about that. And waiting and or delay to take it back into service, from the moment that you find out it didn't work, the moment it worked again, that was the old MTTR. That means the failure is corrected here at this timeline. What has changed? That's a topic for today. By the new edition 2 of the 6.1508, which was out in April 2010, the MTTR is no longer called the mean time to repair. It's now called the mean time to restoration. And some people may say, yeah, it's only a new name in English or a new abbreviation. Unfortunately, it is not. Because the old MTTR, which is the one over here on the picture, the old MTTR is now called the MRT, and the MRT stands for the mean repair time. So still the same theory. From the moment you know it doesn't work to the moment you will actually repair it and will work again, we call that now the MRT, or the mean repair time. There should have been a bracket closed here, but I see that just as usual, I quickly overlooked this and I didn't see that. So there should be here also closing a bracket. Anyhow, the topic is about the one that I here circled in red. When do we know the system is not working anymore? And apparently in the standard, and I will have a specific slide on that, the MTTR is only applicable when you have built-in diagnostics. That means built-in by the manufacturer. The subsystem will alert you that something is no longer available. That means you don't have to wait until it will proof test. Diagnostics, providing the diagnostic coverage, can detect the failure, because you also have something called undetected, but this is here about the detectable failures with your diagnostics built in. From then onwards, you will know it doesn't work anymore. That means that is where the MRT will start. The question is, if there is no built-in diagnostics, when will you find out that the system is not working? Well, often this is unknown. We can purely try to estimate, and said we have our proof test interval divided by 2, which is, by the way, also in the simplified equations or the formulas that the standard have covered in the informative section. So the formulas are not normative. Again, I also have a slide for that, but I will come back on this later when I will see the slide. It may be clearer for you. So the MRT, which is just explained, from the moment we know it didn't work to the moment we repair it, is called the mean repair time. That is here my summary on this. So basically, the MRT only starts when you found out that the safety function is not working. And assume that we are talking about a subsystem like your solenoid, or like, for instance, your final element means your shutdown valve. You will find out this during a demand on the safety function, but basically that is too late, because your safety function will not work. So that is our unknown factor, as your safety function cannot perform as been expected or as per design. Or you will find this out when you do proof testing, assuming that your proof test coverage, of course, is sufficient, because there's also something called proof test coverage. Basically, it doesn't matter how frequent you test. It also matters how good you can test, how many failures can you reveal which are not detectable. I have a small correction to make, and it's also great that some other, let's say, expert or trainers in our domain of functional safety are also watching the webinars from GMI, which makes me the pleasure that it is worth that people are trying to see what we are saying in our webinars. And in contrast to the previous webinar given in November 2022 about the same topic, where we linked the MTTR also to the proof test, this is not, or this was not correct, because the MTTR is only linked to the automated diagnostics. And I refer here to the reference of Harvey Darden, and Harvey also with the website link. You can check check this out because Harvey is also having a tool called the SIS Suite, which is one of the SIL verification tools. And it came from Harvey with a personal message to me saying, Tino, I think the MTTR that you mentioned is not correct because it is not linked to proof test, only to diagnostics. Therefore, here, this correction. And again, thank you to Harvey for that. So the new MTTR, which we just have seen, again, comes out of this report number 2 from the ISA 84 committee. And if you read that document, they also explain why the new standard edition to 2010 has corrected the MTTR from the old days to the new one today. And the new one today has been adopted by the IEC 61511. That is why we have today here this webinar. That means we have the same concept on the MTTR today in the process industry as also the 61508 edition to 2010 has been released. So the unknown time, which we have already mentioned, when you have no diagnostic coverage, the unknown time in that document of the report 2 from the ISA 84 has been referred to a mean fault detection time, which is coming from the ISO 12489, which warns you that the actual time spent to detect the fault is never known and cannot be collected, unless, of course, you have a good proof test coverage and a good proof test procedure that you will reveal that failure. The detection delay term here, and this is now what is maybe for some of you, including myself, is not really what we like to hear, but the detection delay term has traditionally been neglected from your PFD average calculation. So if you think about that, the MTTR is only applicable on the subsystems which have diagnostic coverage. And the question is, for those where we have no diagnostics, why don't we actually, in our estimate of availability, take care of the time that we need to find out that the system has not worked, or if it is not working, the time that we need to repair it again. MTTR is only applicable for subsystems with diagnostic, as I just mentioned, which basically, frankly speaking, it doesn't really make sense to me, since those diagnostic coverage are all in milliseconds, seconds, minutes, seldomly found in hourly, let's say, time interval for diagnostic coverage. Is typically a lot faster. I'm thinking like, for instance, your safety PLC. Your safety PLC, typically based on the scan time of the CPU, providing they can execute the complete diagnostics in one cycle, that will be milliseconds. Your smart and hard transmitters, also based on a microchip on the PCB board, also have a cycle time, so also that will be in milliseconds. There are a few exceptions on systems which have a longer time, but those are all very, very, very frequent. First of all, they are frequent. Secondly, most likely those sensors or those safety PLCs will be built in a certain configuration which is redundant. That means even though they have a failure that they know they have, they can actually degrade into a lower architecture, and they can go into a subsystem architecture where they know the known failure may be switched off, and they will refer to the ones that are still working. That's all examples that I will later on come back when I have the specific slide. Yes, Maro, let us ask the first poll question and then we can continue.
Yeah, I launched. I think you should see the question.
So diagnostic test interval and MTTR. And the question is, A, when diagnostic test interval goes up, your MTTR goes up. That is the first answer. B, when diagnostic test and MTTR have nothing to do with each other. That is your answer B, potential. C, when diagnostic test interval goes up, your MTTR goes down. That's answer number C. And the last one, MRT is MTTR plus diagnostic interval time. That is answer D. So I would recommend for those who haven't clicked yet, make your vote. There's no points to win or to lose. There is also no money to gain or to lose. So it's risk-free. You can just click. We just want to have an impression. What is your idea about which one of that for answers is the most complete and the most correct one? And I see, Mauro, that we nearly reached half, so I would like to have a few more clicks.
Yeah, let's.
Yeah,
Here we are.
It's still going in, so it goes in the good way, in the good direction.
Yeah, maybe it was not such an easy question. We need to think about.
It's the
Okay.
learning also. Okay.
I think I can stop it here.
You can stop the poll and you can share it if you want, Maru. All right. So I hope that everyone can see the shared result. We see here that the majority of you have answered the first answer. When diagnostic test interval goes up, your MTTR goes up, which is of course 100% correct. Because for those who just have listened, the unknown time is not unknown if your coverage factor from your diagnostics based on your diagnostic interval actually can detect the failure. From then onwards, we know it doesn't work. And from then onwards, we are starting the MRT, which is the mean repair time. But when you take your diagnostic interval, plus you take your MRT together, that is your MTTR. The second answer, diagnostic test and MTTR have nothing to do with each other. Of course, we didn't mention diagnostic test interval or diagnostic test coverage, so B answer is not correct for many different reasons. The C, when diagnostic test interval goes up, the MTTR goes down. That's just the opposite. It should also go up. And then the MRT is the MTTR plus the diagnostic test interval. This is also wrong. It should be the MTTR is the MRT plus diagnostic test interval. Therefore, A was the only correct answer. All right, Mauro, let's continue. So, topic for today is related to the 61511. The introduction has been given based on the old edition before the old MTTR definition before the IEC 61511 edition 1 was out in 1997, has been reviewed in 2010 in April. That means our latest edition today for the process industry 61511 has also adopted the same concept. Text is all the same. MTTR, MRT is idem dito, or it's all the same as in the 61508. What we also have in the 61511 edition 2 today, we also have the maximum permitted repair time. That is the maximum duration allowed to repair the fault after it has been detected. For instance, we have the theory concept, how long will it take us for us to repair it? Opposite, on top of that, we cannot, not opposite, on top of that, we can also say, yes, we will estimate it will take us 8 hours, but what if the subsystem is not available? What if we don't have it in spare? What if we have to order it and there is a big delay in delivering times? Well, that needs to be estimated if possible and saying what is the maximum permitted repair time, because it cannot be correct when you have a SIL X qualified, let's say, safety loop, that you say, well, the subsystem has failed, however, we have to order it and we have a 3 months waiting time. The question is, how will you compensate for the subsystem which is no longer available to reach or achieve your safe state on your safety loop? Proof test, which we already mentioned, the proof test means that for all those failures that cannot be detected with built-in diagnostics, for all the other subsystem failures, the engineer will have to reveal the failure, so we don't call it detect the failures, reveal the failures for those who are potentially dangerous and those who are also potentially safe failures. Enable for us then to estimate and to say how available is my safety loop. We are required to document the fair behavior of our safety loops based on the 61511 requirement. And for that, of course, we need all kinds of information. And I yellowed here a few ones. Of course, we need the proof test interval. We also need the proof test coverage. And we also need the MTTR and the MRT. So those are all times that we will need to fill in our most likely commercial SIL calculation tool. And based on all this data we enter, the result will tell us how unavailable, predictive will be that safety loop. In other words, what is the PFD? The problem that we have since 1997 until today, it means in all these years of wisdom and industry experience, there is no, and I repeat, there is no normative formula in the standard that everyone around the world will use the same method to predict the unavailability of their loops. That is good news, that is bad news. The good news is no one can prove you are wrong, because simply there is no reference, hard on cast on paper, there is no normative section and standard to tell you that is how you should calculate or shall calculate. They only give examples, and the examples are from simplified, let's say, formulas in the informative section. And the word informative is here the bottleneck, because it is informative, it is not normative. That means the bad news for us all is that everyone is trying to estimate, everyone is trying to calculate, and everyone has his own idea on how to do it, or is based on a commercial package. But there's no one that can prove you are correct. There's also no one that can prove you are wrong. Beware that the IEC and even the ISA, they both have a different vision on the simplified formulas that you may use. What will be now the challenge for you and for all of us? Well, when GMI is selling these interfaces, which are SILP compliant subsystems, GMI, of course, has also a liability towards the functionality. GMI has also a prediction how long it will work before the system potentially will have a failure. That is the famous bathtub curve, which I will not go into depth now. But before the wear out would kick in into any subsystem functionality, there will be a predictive, let's say, time that it will work. So shorter than the time that they will know that it will work. Let me give you an example. Assume that one of the modules of GMI may have a lifetime of about 20 to 25 years. GMI may want to take some liability margin and will say, well, we recommend you, Mr. End user, or the person who will use that, let's say, subsystem, we recommend you that after 20 years to prove that the system is still working. Therefore, if you go into the GMI safety manuals, the safety manual is a normative requirement from the IEC SIC 1508. In that manual will be clearly explained on how and how frequent you have to test. In other words, the proof test coverage will be explained and the proof test interval. This is not the proof test interval that maybe your SILP calculation tool may estimate, because that may be more frequent, because there you will look at the mission time of your safety loop, and based on the mission time of the safety loop, you may have a specific, let's say, proof test interval that is potentially short. So, continuing, the 6.15.11 report number 4 from the IEC 6.15.11 is another point of confusion regarding the maintenance, is relating to facilities desiring a long test interval. In other words, when you have, for instance, you have facility where the production management, production engineers or operators are telling the safety engineer, you are not allowed to close the valve in the next 5 years. Why not? Because we are not allowed to stop the production. If for that reason, for instance, the proof test interval, which was required on paper, is every 3 years, but production is saying, no, we cannot do it before 5 years, well, then we do have a problem. So the standard is now saying SIS devices, SIS devices, which are not able or not allowed to be proof tested at a design frequency due to production availability requirements, are not fit for purpose and needs to have a redesign, which is a very strong statement to help the safety engineer in a discussion with the production responsible people to say, listen, it's not down to the production requirements how long this system needs to work. If the proof test interval is shorter than your requirement that you want to use it, something is not correct. Right, Maro, we have a last poll question for today, I think, or the second last. Which one of the following statements is correct from an end user operating company point of interest? Which of the below statements?
Launch it. You should read it. You should see that.
Yes, I did. I do.
Can you see that?
Yes, we see it now, or I can see it. So from an end user point of view, an operating point of view, which of the following statements below is the most complete and the most correct? The manufacturer of a subsystem can estimate the MRT, which is the mean repair time. That's the first potential answer. Second answer is only the end user operating company can estimate that same MRT or mean repair time. Then answer C, the manufacturer of a subsystem can estimate the MTTR and the MRT. It's okay. I see the first answer coming in. Finally, I was already getting scared because no one was reacting. So the manufacturer of a subsystem can estimate the MTTR and the MRT. That's answer C. And the last answer D, the end user operating company cannot estimate the MRT and MTTR in function of the required risk reduction factor. It's quite a tricky answer selection that you have to go through and able to select the right one, but I still hope that you have a fair chance to select the correct one. And it's purely for us evidence. It's not evidence how many are still awake. It's more evidence how many actually are following the topic, because the answer has been given a few slides before it. We were doing good, Maro. Seems that
Yes.
the audience is still interesting to click, so it's good. And again, we have the 4 answers are all clicked, and only one of them is the most correct and the most complete. I think, Maro, we are about there. We could...
Yeah, I can stop it and share the results so that you can comment on that. All
right. So the answer A was clicked by someone saying the manufacturer of the subsystem can estimate the MRT, which is, of course, not correct. As an example, GMI cannot estimate how long an end user in country X will take to repair a broken subsystem from them, right? They can only give recommendations of testing and all that, but they cannot estimate how long it will take to actually have your mean repair time defined. Answer B, of course, was the only correct one. Only the end user and operating company, based on, for instance, some end users will work with a service contract. That means that they will have a service contract because of manpower problem or budget problems, whatever. That means that they will have to demobilize one of the service engineers on site based on the availability of the subsystem replacement in the warehouse, yes or no, or maybe inside their service contract. Well, that will be then be estimated how long it will take for them to actually repair it or to restore it as good as new. While only the end user, of course, can estimate the mean repair time. The manufacturer of a subsystem can estimate the MTTR, which is correct. That is the MTTR itself. However, it's based on a parameter that needs to come from the end user itself. Now, if you see that that the manufacturers like GMI will estimate the MTTR, that is purely based on a theory that the subsystem is available, that you will be alert the subsystem is failing, and that you will be replacing it in the given time which they have based their theory on. But the real time is always coming from the end user. So the last topic, the end user operating company cannot estimate the MRT and the MTTR in function of the required RRF. It's partially not correct. That is why the MRT, yes, the MTTR, it's all depending again. Do we talk about the MTTR in general? Do we talk about the real MTTR, which is based on diagnostic coverage or test interval? Or do we talk about the MTTR, which I already explained you, on the unknown factor, which may be your proof test interval? Right, Mara, I will stop sharing that. We will finalize with a summary. Well, with the summary now, all this theory, all these definitions of timing, the MTTR today, in the new edition of the standard, both 61508 and 61511, is related to from the moment we detected that the failure was in the system. That means we detected that with a diagnostic coverage. It's not correct when there is no diagnostic coverage in there. That means the unknown factor comes into play. I simply wrote here, or I simply explained here the time A, B, C, and D, which I will not repeat because we have done this before. But I have one last slide, which may be of interest for you. And these are just some pictures of some instruments. Of course, we have here a GMI barrier. We have here a GMI safety relay. That means that from a single safety loop, from left to right, where we have a safety instrumented function, we have a sensing device, which may be your smart or hard transmitter, going over a isolator into a safety PLC with an interlocking solving program. That means you try to solve some interlocking program. Based on the result of the interlocking program, you will send your digital output into a safety interposing relay here from GMI. And from that relay, you go to take the power away here from the solenoid, and the solenoid will actually here try to close this valve as a failed to close shutdown valve. So in reality, the question will be, from all the pictures of all the symbols of all the subsystems here in the safety loop, those who have no diagnostic coverage are typically the final ones, which is here the final elements from the solenoid starting to the final element itself, meaning your shutdown valve. And statistically, from the industry, the failures representative part of a safety loop not working, 50% is always coming from the final element sections. And in those, we have no diagnostic coverage. Whereas those where the other 50% is coming, so from the sensor all the way to removing the power here with the safety interposing relay, that represent about another 50% of the failures. That here is typically, oops, that was too quick. That here is typically based on diagnostic coverage, most of them. That is typically based on internal, let's say, redundancy, hardware fault tolerance, etc. And for those that we do know the failure, that we are alert that they are not working and that we can degrade into redundancy, for that is where the MTTR is coming into the picture. For the last one, where we have no idea until it is too late, that means until we are testing it and then we find out that it is not working. So it's not too late yet in the sense of you didn't need it yet, but you will find out when you are testing. When it is really too late is when the safety function is trying to close that valve to find out the valve is stuck open. That is where we have a problem. Now, I know that there is some theory also by some vendors and by some calculation tools to take some, let's say, credit for departure stroke on a valve. Classically, the departure stroke test on a valve is only there to try to reduce the full stroke interval. That means we're putting in a departure stroke on a valve to reveal partially some of the potential failures, in the hope that by revealing some of the partial failures, we will estimate that at least those are still working. The other ones hopefully will not stop us from achieving the full stroke or let's say the safety position. But that is purely a theory which doesn't make the valve safer. It is purely taking away some of the potential danger failures on that valve by proving them in a partial stroke. Right. As Mauro was saying, one of the last products, which is not a hardware product, is more a service or a training. We are providing services. So one of the services is that we have a IEC 61511 lifecycle support with different topics. And we also have it now on the cybersecurity, which is the 62443 OT cybersecurity standard, which is for industrial security management and assessment. We are helping some, let's say, projects with. Plus also we have in the meantime some supplier security management that we are helping with. We're also providing both virtual and classroom instructor-led training. Actually, as a matter of fact, last week for GMI organized, there was a full class in Rome with one of the leading EPC contractors that we had an in-house training with 20 people. So we still provide them in class, but also next week I'm starting a virtual training, which is the same training, but then online. So we have people from all over the world joining with different time zones, but they join the training that we put in a specific time zone, which will be here now in this time. In this case, it will be the European time. So the TOV Rijnland accredited competency review programs for functional safety, for cybersecurity, both the fundamentals and the security risk assessment training courses. With the last two bullets here, the cybersecurity fundamentals and security risk assessment can be combined together into a full week, means in 4.5 days now. We provide customized in-house training. I was a couple of weeks ago, I was in a waste treating plant in Europe, giving a in-house functional safety one-day training for them. We also have more GMI webinars that will come up. And as Maro is saying, they all recorded. Some of you may have here this famous yellow book. I call it the famous book because there are more than 50,000 copies worldwide, which you come across always some training that one engineer will pull it out, said, I got still the 3rd edition or the 4th edition. The good news is the book is still available. You can contact GMI online and able to try to request one of those books. And I will stop it here, Maro. I will stop sharing this and I will give it back to you, or I have to go into
into the question and answer.
Yes, I will go into the question and answer, which were already collected. So what we did was we collected. So let me also start this, Maro. It's maybe easier for you. But now I lost my, hang on. I lost my Zoom. Where is Zoom? Zoom is here. Okay, let me share that screen, which I just showed. This is the Q&A, and now say share, and now do this again. And if everything went well, you see now the Q&A starting.
Yes.
Correct? All right. So what happened was there were a few interesting questions that came in during the registration, and simply I picked, of course, the most accurate, or so the most relevant, not accurate, the most relevant questions out of there, and I have prepared some of the answers. And the first question was, do we need to take the MTTR in proof test coverage or not? Of course, it's never easy for us to say to how do you say that? To try to think in the brain of the engineer who asked that specific question. I was wondering why this question came in relation to the MTTR in proof test coverage or not. And then I said, well, actually, that doesn't make sense since your proof test coverage is a quantity, it's a percentage. How many percentages of the failures I can detect are actually potentially based on diagnostic coverage? That means those who cannot be detected, we call those the danger undetectable failures. And those are the failures that the engineer will have to reveal based on the proof test instruction explaining what they have to do. And this comes mainly out of the safety manual, like I mentioned already to GMI safety manuals. They will explain you do test 1, 2, 3, 4, 5, and then you can claim, as an example, 30% proof test coverage. If you do the additional 1, 2, 3, 4, 5 test, you can claim the 90% proof test coverage. In other words, the specialist vendor developers from hardware/software specialist, they will explain you what you will have to do in able to claim a certain proof test coverage. The MTTR is nothing to do with the proof test coverage. The MTTR is a time giving, as we already explained. How long will it take from the moment that the system is actually failing to the moment the system is working again? That is the time here from the moment it fell to the moment it worked again. There's always this unknown time in there, or we have the time in there that is your specific proof test interval. The interval is a frequency, but the proof test coverage is a quantity, is a percentage. Right. Interesting uses of MTTR in silk calculation. So this is a very relevant question, as I just have given you the slide, but I'm just repeating this because I thought the question is very relevant. Referring to our summary in the webinar, the MTTR is only in relation to a subsystem with diagnostics. In other words, the ones that were all here in the front, the ones which are not circled red, means those are most likely covered with MTTR, are most likely have built-in diagnostic, let's say, interval/coverage. Where those where we typically struggle are the final elements, and also represent, for a specific reason, more than 50% failures in the industry in your safety loops. What are the reasons pushed to change the acronym from MTTR definition from mean time to repair to mean time to restoration? That was also already answered, but I'm repeating it here. The second edition has done this of a 61511 following following really the footsteps from the edition 2 of the 61508 from 2010. And the real reason was that they added here in that story, they added here that detection delay, and that is also most likely why the MTTR is only in relation to diagnostic coverage / interval, not in relation to your proof test interval. So the proof test interval would be potentially, not always, could be potentially the unknown, and you have a demand on the safety loop and then you find out that it's not working. But if you have tested before and you found out, hopefully you will find out before it is too late. Well, that is where they have neglected the MTTR in that PFD calculation. We have one more question by memory. How the MTTR value impact the selection of a SIL certified product? And I found this an odd question. I thought like, well, I'm not going to answer that because it's really odd. And then I thought like, well, maybe it's not so odd as because we are maybe too stuck in our own functional safety world. Maybe think about someone who has to make a selection, who has to buy a specific product. How do you actually select your SIL compliant subsystem or product or interfaces? So imagine you can select a subsystem, which we call here not a SIL certified product, we call that a SIL compliant, or it is suitable to be used in a certain SIL performance band. And imagine you can select a subsystem with diagnostic coverage of more than 90%. Means that in theory, that subsystem will detect for you 90% of all potential detectable danger failures. That means that MTTR time, which is not a theory based on those detectable failures, will start from the moment the 90% will be actually detecting the failures and alerting you something is wrong, to the time you can repair it. That would be a benefit for you, that 90% already detected. That means there is a rest failure of, in theory, less or equal to 10%. Of failures which are dangerous that you will have to reveal. So we don't talk about detected failures. That means you need to reveal those failures because diagnostic detection could not be detecting it for you. That means about the 10% which are still rest failures in that subsystem, you will need to have the sufficient proof test, which is here abbreviated as PT, proof test coverage, and proof test interval enabled to reveal that failure. And from the moment you reveal it, you will have to have the right, let's say, procedures and availability and allowance to go and repair that. Summary, I would search the SIL compliant product with the highest diagnostic coverage available on the market. That's also why, if you think about that, in reality, in the market, there are not many safety, let's say, compliant subsystems available with a safe failure fraction and or a diagnostic coverage lower than 60%. Because lower than 60%, they would struggle even to reach a SIL 1, depending if it is a type A or a type B based on that 61508. And with that, Mauro, I think I'm right in time. It's right in the hour. So
exactly right in time. We ask our audience to provide us feedback on the way we have done the topic, and as mentioned before, you will get the PDF file of this presentation with our contact. We are always keen to have your feedback. Last time was happening that we received a lot of specific email thanking about the transfer of knowledge that we are providing. We would also like, if you don't mind, to get your recommendation maybe for specific topic that we may think about to extend our content of webinar. Before to say you goodbye, I would like just to remind that this webinar, together with all other webinars, will be available on GMI YouTube channel. So if you believe that you have missed something, you have the chance to go back and to check, or maybe you will find topics that are of interest for you, as well as the invitation to watch our website, where we provide a schedule for the next webinars on the different topics that we time to time touch. Again, and a special thanks to you, Tino. Always pleasure listening to you. Even we are repeating the same webinar, or sometimes we repeat the same topic. It's always something new that I'm learning, listening to you.
Good.
And I look forward really to meet you in person as soon as possible. And again, have a good day to everybody, and thanks for sharing your time with us.
Need to share this poll quickly. Let me see if I can share the results. So thank you, Mauro. Thank you, GMI, for giving us.
Thank you for the feedback as well.
And keep it safe. Thank you. Bye-bye.